Yeah, definitely.
Worry about
But it's still something you have to compare the cost and stuff like that.
Yeah.
So we like this. Great, so let's get started. So welcome back, everyone. So let's look at the schedule. So hopefully everyone turned in the clustering assignment. That means you've done half the assignments for the class already. So we're much less than halfway through the semester. You've done half the assignments, and I think you've probably done probably 3 out of the 4 hardest assignments as well. All right. So I mentioned last week the frequent items assignment has been posted. I think that one should be simpler than the clustering one as well. And then the ones after break are also, there are only 3 more after break, and those should also be shorter as well. So I think you've done kind of most of the hard work for assignment. You're still going to have more assignments as we go through material. It's part of the learning process and so forth. But I want you guys to focus a bit more on the projects, right? So you'll see that we're still working through the feedback on the day collection reports, but there's going to be an intermediate report on that'll be due on the Monday after break. Actually, in that lecture, the lecture in class today, you guys are going to be paired up and discuss amongst other groups, just to give you some self kind of intergroup feedback on your projects. And then that first week after break, you're actually going to meet with me. You're always welcome to meet with me after class and office hours and all that stuff, but all the groups are going to actually meet with me for a few minutes, and you'll get some kind of specific directed feedback on what to try and do to finish on, right? So, so hopefully you start getting us kind of a start on those projects. And the goal is at the intermediate report to have enough to kind of intelligently discuss with me about how you're doing so far versus and how much you expect to do. Some groups will be, you've already done a lot, you don't need to do that much more. Others are like, yeah, you kind of have to get going. And hopefully I'll be able to kind of give you fairly specific advice. Try this differently, or this or that, or if you do this, then you'll be this one more thing, you'll be in good shape, right? We're going to have the second lecture today on kind of the large-scale data with streaming approaches, and then there's going to be this lecture here, the second Monday after break, is also going to be on streaming, but have to do with kind of some of the regression and dimensional reduction ideas. So we'll wait till after those have been introduced. But they're going to build on ideas that we covered last week and then today in the lecture. Great. Oh, and then the midterm test is looming. It's going to be in class as well. It'll cover up through today's lecture. Okay. Well, crashed. And okay, so we're talking about streaming, and we're going to introduce a new approach to kind of a new kind of paradigm of streaming, ones that use these like randomized approaches in order to kind of capture stuff with the stream. And they're going to have a distinct advantage over all the ones we talked about earlier, in that they can handle actually having deletions in the stream as well. So the idea here again is that we're going to have this stream of these items, A1, A2, up to say AN, and each AI is going to be in is going to be in like some sort of domain. Let's have this go up to M. And then the challenging part of the streaming, so this is just the data set so far, but the challenging part of streaming is that we get one pass. We only get to read the data once. So this could be like you have an algorithm which is operating on some sort of router, and the packets are just streaming through, or you have this large file on disk or in the cloud and something, and you can't fit it in memory, but you're willing to spend the time to read through the file once. And so you bring it into memory, you read through it, you calculate something, and so there's one class and small space. All right, and so what's going to happen is you're basically going to kind of convert this stream into some set S or some sort of object X, which is going to have this like small space constraint. And so this idea of taking a data set and converting it to something that has much less space but captures the core elements of it is important across basically any paradigm that deals with very, very large data sets. We talked about there were three. One was you just sample from the large data set. Well, that would be one instance of a much smaller data set. It's just the sample, right? The other one is doing something in parallel or across multiple servers. And then the challenge is you actually have to, the core cost is communicating across these servers. And then you don't want to communicate all the data, you want to communicate some summary of the data and get some answer using that way. So again, you want to kind of understand the small space requirement. And so, and then in streaming, this sort of comes naturally. And so this kind of idea of how do I take a large data set and convert it into a small data set that captures information comes up a lot of places, but I think the reason we study streaming is that it's a pretty reasonable and it's like a simple model for this, and it captures almost all of kind of the interesting aspects of it. So almost all these algorithms kind of, you can apply them to more complicated, fancier scenarios that have more kind of parameters to them. This is pretty simple. I make one pass, I have small space. Okay? And so here we have the idea that n is like very large and m is very large, but log n and log m is okay. And so these correspond with, this one corresponds with like a count, and this one corresponds with like a label, right? So I can take if I look at an element of this set, M, there are M things, M IP addresses, or possible kind of kgrams, something like this. There's this huge number, but I only need to kind of have one label of one, and that takes log M space, and to kind of keep a count of how many things that thing's seen, that's log M space, right? So something on the order of log N or log N is okay, but N and M are just too big to store. I can't store everything that passes through our store router, or the data is too big to fit in the memory. Okay, so and then we were talking about these like so these objects like for frequency, and let's say J is an element in here, and we'll say that Fj is then going to be the set of all the elements in the stream such that A is equal to J, and this is the size here. Okay, so we want to, this is the frequency of the jth element, how many times, say, the IP address J occurs, how many times the certain kgram J appears here, right? And we want to approximate all these. We're going to, again, approximate them. But I want to kind of talk about a couple of other characteristics here. One is that these are often summarized with uppercase F, and these are more aggregate statistics about the stream. F1 is just going to be the sum over j of fj. This is equal to the total count, and this is always m, right? Sorry, not m, n. N, this is the number of things in the stream, but there are other versions of this too. The f2, fj squared square root. Okay, so this, this is another way of computing the total size of the stream. This is more like it is more like the L2 norm. And so which one of these you think is larger or smaller? F1 or F2? So if we typically have this over a stream, one is just adding up the counts, one is squaring each of the counts, and I add those up, but then I take a square root of that. Huh? Yeah, so typically F1 is much larger than F2. Okay, so this is relevant because we basically, the bounds we wrote for the Michel-Gries algorithm last week was in terms of epsilon times F1, epsilon times n, kind of the total count. This is much larger than a bound times epsilon times epsilon, the epsilon times F2. And so we'll talk about an algorithm today that gets bounds that looks like this. It looks like the space is larger, but the bounds are in terms of the F2 term. And so basically, the more skew there is in the data set, the more kind of, if there's a small number of elements that have lots of the count in them, which is kind of basically the case in your homework assignment, then the F2 is going to be much smaller than the F1. And this typically occurs in like actual data. There are some IP addresses which I think there are some IP addresses which probably aren't even assigned, right? So they don't have any counts to them. But there are other ones that get lots and lots of traffic, right? And certain k-grams are going to be much more frequent than other ones. Yeah.
The way you've written that sum, you're saying total count of n, but it looks to me like you're taking the sum of every element in the set that has that value.
Yeah.
I'm trying to just differentiate between how many there are, and then the sum, and then the squared.
Yeah. So let's say again alphabet A, B, C, D, E, F, right? And well, F will be confusing. Let's so like stop at E, and we'll say that the frequency J, and this is going to be J. Okay, so J is going to be A, B, C, D, or E, and I'm just counting letters in some small alphabet, right? And so I can see in the stream, let's say it's 7. So if the stream is something like A, let's not make it 7. My example is too big. Okay, let's say the stream is A, B, B, C, A, E, B, C. Okay, then I can have counts for A is 3, for B is 3, C is 2, let's add D here, D is 1, and E is 0. Okay, so the total count of the stream, 1, 2, 3, 4, 5, 6, 7, is 10, n equals 10, and 3 plus 3 plus 2, 1E, yeah, good. Well, 1E here. If I add all these up, it's also 10, right? So I'm accumulating them into these numbers, and then I'm adding these up, right? So it's still the total count, it's just a different way of counting it. Yeah. And then let me write up one more that's interesting. Let's say I do fj0. I raise it to the power 0. What is this capturing?
How many different items are?
Yeah, so this is equal to the number of distinct items. Okay, and so this one turns out to be even like this. This one's even harder to kind of to kind of work with, because I don't want to keep account for each thing. So if I haven't kept track if someone was there, you know, so how do I, if they appear again, do I say, well, that number incremented, or it's the same as someone that I've seen in the past, right? So if you're a website, you want to keep track of the number of distinct users you have without keeping some object for each user, then you know you want to estimate this quantity, right? We aren't going to talk about the techniques for doing this, but they're kind of in the same flavor of the things we'll talk about today. You basically have to use some sort of randomized algorithm. You can't do a deterministic algorithm like we did last week. So estimating this is harder. Estimating F2, yeah, there are ways also to estimate F2. We aren't going to give them in this lecture. You can do a whole course on these kind of on these sketching algorithms. Yeah.
When you say harder, you just mean like you have like a wider confidence interval, basically, or what do you mean by it?
Oh, the algorithms are more complicated, and the reason why they work is like more convoluted. You keep track of multiple things, and you take the difference between them, and it kind of works out. So it's kind of these, the ideas we're covering in this course are, I think, going to be more intuitive, are hopefully fairly intuitive things. We're introducing concepts like approximate data structures and approximation guarantees in various ways, which I think are enough to learn on this pass through this material, whereas these ideas are more complicated. Great. So the goal, again, we're going to talk about so frequency approximation, and so then for all j in this so in this domain, I want to be able to kind of return an answer fj, so that fj minus fj hat, so fj is the true value, is at most epsilon times f1. Okay, but we're also going to describe an algorithm where it's going to be at most epsilon times f2. Okay, so this we'll describe the one with the second bound second. That one is going to appear. Its dependence on epsilon is going to be worse. This one has going to be it's going to have size 1 over epsilon times some poly of log n log m. Okay, so some so I think it's linear in those. Whereas the size for this one is going to be 1 over epsilon squared times where it's got some polynomials in the size n and m. And these will have to do with kind of, I don't want to write them down specifically, have to do with size. The size to store like the size to store a hash function, and there's some pretty tricky details in there when you probably are just going to use a built-in hash function. Yeah.
Epsilon here, it's just like the amount of error that we're allowed.
Yeah, so we're allowing some error tolerance here, and think of epsilon like 1%, right? So if you want And with the F1, remember because F1 equals n, then epsilon F1 equals epsilon so percent of the count, right? So I'm off by 1% of the total number of packets I've seen in the stream. Whereas with F2, it's a different quantity. That's a little bit harder to grasp. There's a notion of the self-join size that you might see in a database class. That's what F2 captures, if that helps. Yeah.
Can we go to that first line? What is that arrow indicating there? What operation is that?
Oh, okay. Yeah. So I want to talk about that. Yeah. So the idea of a sketch. So we're going to have some sketch of A, right? So this is going to be a little bit more complicated than we had with the Mischigre's algorithm, although that counts as an example of this. And think of this as a data structure. Okay, so it's a data structure that I can put things into, and I can basically do insert some element of the stream. Right, so I can insert some element of the stream, or I can ask a query. Right, and so on the query is going to output some FQ. So if Q is an element of M, then it's going to output FQ hat. Okay, and it's going to have some sort of guarantee on the accuracy here. Okay, so it's not going to, I could think of building a data structure so that I can answer the exact answer. I could answer the exact FQ, right? So I can build a data structure which is just kind of a counter. I have a counter for each element, each of the 1 through M kind of different elements of the domain, and then on a query, I just return the value of the counter. But this takes more space, so so it's going to have a trade-off between the space required for S of A and versus the accuracy, which will be captured by this term epsilon. Okay, so an epsilon will either be kind of, all of them will be off by at most epsilon times F1 or epsilon times F2. Okay, and so the Mischigre's algorithm gave us it gave us an instance of this, where if I ask a query and I have a label which matches the query, then I return the value of that counter. If it does not match any of the labels, the query does not match any of the labels, then I return 0. Okay, and this gave me this epsilon times F1 sort of accuracy, and the larger the number of counters, the more space I needed, but the more accuracy I got, right? So the smaller was epsilon. All right, so that one had a value, so it was always going to be an undercount. We're going to talk about two algorithms. So the count min sketch is going to have the property that it's always going to be an overcount. So Fj is always going to be less than Fj hat is always less than Fj plus epsilon times n. And we're going to talk about the count sketch, which the count sketch is not going to have, could be an overcount or it could be an undercount. So I could say that Fj minus F2 is less than Fj hat Fj plus F2. Right, and so this one's going to have error with F2 instead of F1 here, which is just n. Okay, these are also going to have another accuracy parameter. And these are going to be true with probability at least 1 minus delta. So I'm going to have another accuracy parameter as well. So they're going to be randomized algorithms, and so this is going to be their probability of like failure. So I'm going to have these accuracy bounds with 1 minus delta probability. This delta term will be kind of pushed inside of a log of 1 over delta. So I can actually, it turns out I can set this pretty small without having too much penalty. Okay, so I can set the probability of failure to be pretty small without too large of a penalty. The epsilon term is the term which is usually dominating this relationship. But because they're randomized, I have to pay attention to this extra term. Yeah.
Is failure just defined as it's outside of the error term?
Yes, it's outside the error terms. And it turns out most times if it's outside the error terms, it's just barely outside, but we usually just write it this way. It's harder to write something as like specific that if we need a bunch more kind of parameters, or say it looks kind of like a Gaussian in some way, and kind of there's some form of central limit theorem going on here, and this is kind of what's called probably approximately correct. So it's probably with probability 1 minus delta, approximately with error epsilon, so correct. And you need both of these terms. Okay. Good. So let's okay. So with this sketch data structure, I've not told you yet how to return this estimate. I told you with the Michel-Gries algorithm, but we're going to have a kind of a very sort of different mechanism with these algorithms instead. Okay, so it's going to be more of a more kind of I'm not just looking at one counter, and if it's there, return the value of the counter. I have to do something slightly more complicated. Okay, and so that's more common among these when you hear something as a sketch data structure. It'll be a little bit more complicated to retrieve the query. It's still fairly simple, but not just, okay, let's find the one counter it matches and return that. Yeah.
What's the motivation then for moving beyond Michel-Gries? Like, what does this give us in addition?
Yeah, so sometimes the count sketch is is better than Michel-Gries. This one is, count min sketch is almost always going to be slightly worse in terms of this trade-off. The advantage is that I can also do a deletion. That's kind of the main advantage. There's another paradigm where, let's say I needed to do a correction on something I saw before. I passed something, I inserted something in the data structure, and after a few more inserts, I realized that was actually a mistake. I don't know how to unwind the Michel-Gries one, but with these, it's very simple to update. And this makes them very flexible. Things like you can do addition and subtraction within these models. So instead of having just a stream of elements, I can do streams plus some value, and the value could be negative, right? So let's say I'm keeping track of people coming into the classroom, and people are coming in, and then they're also sometimes leaving, right? So when someone leaves, I have to remove the effect of that person, right? And let's say I'm keeping track of something like the total age, or the average age, or the variance, or one of these other things we talked about before. Well, if I have to subtract someone who comes out, I need to unravel kind of everything. With these, it's going to be very natural to kind of do these more complicated updates. And so they become more flexible, and there are different ways that you can use them in terms of. Like other than just subtraction, there are other kind of more complicated things that we won't get into that these are sometimes useful for that other ones aren't. And then we'll see examples with the matrix sketching, which will build on the Michel-Gries and on the count sketch, and they lead to fairly different algorithms with different sort of advantages. This one turns out to be much, much faster for the matrix sketching than the Misch-degrees, but maybe not quite as good error, and there's various trade-offs. Okay, so the count, min, so sketch. All right, so this is going to, again, start with, I'm going to say, I'm going to have k of these like these counters. Okay, so I'm going to call them C, say 1, 1, C 1, 2, C 1, 3, up to C 1, K. Okay, so I'm going to start with these counters, and instead of saying K equals to 1 over epsilon, you have to set it to 2 over epsilon. Okay, so this is how we'll interact with epsilon. I'll just put this up there now. So I'm going to have counters like I had before for the Misch-degrees sketch, but instead of just k counters, I'm going to also store t of these so t of these hash functions. Okay, and so t is going to be log of like 1 over delta. So this is going to handle my probability of failure. And actually, instead of k counters, I'm going to have t times k counters. Okay? So what I'm going to stack them in this table. So it's going to be C2 1, C2 2, C2 3, up to C2k, down to CT1, CT2, CT3, up to CTK. Right, so I'm going to think of having this table of these counters. Okay, so and then for the t hash functions, these are going to be and these hash functions, each of hj is going to go from this domain M, and it's going to map to this domain K. Okay, so it's going to map to kind of in each of the rows, it's going to match to one of the counters. So I'm thinking of putting these here, H1, H2, up to HT. Okay, so this is going to be what the data structure is. I'm going to have these hash tables, and you kind of imagine you have some element come in, and with the hash table, it maps it to one of the columns, and there's a counter there. Okay, so I have to handle two operations. So the first one is insert AI, right? Remember AI, I think I'll use I, so we'll say A in the stream. And remember, A is going to be equal to J, which is, let's say, it's going to be equal to some value Q, which is in this domain. Okay, or I don't think we need to specify. Okay, so A is going to be in this domain M. Okay, and so what I'm going to do is I'm going to insert A, this stream element, into each of the rows. Okay, so for J equals 1 to T, I'm going to find this counter in the jth row, and I'm going to find which counter I'm going to hash the jth hash function of A, and I'm going to do an increment on this counter. Okay, so again, this notation is kind of capturing a lot which is going on here, but basically I'm going to hash. So as A comes in here, and I process each of these rows, and it's going to hash to each of these counters. And it could be that it hashes to, so each row, it hashes to exactly one of the counters, and it could be it hashes to the same column twice. That's fine, right? Some columns it might not ever hash to. So probably k is larger than t, right? Think of t as like 5, and k is like 100. Okay, so it could hash to the same column twice, but that's not going to matter. These rows are essentially going to work independently, right? The hash functions are going to be deterministic. I've chosen the hash functions from a family, right? But they're deterministic, so that means if this is a certain IP address that comes in, I see it twice, when it comes in again, it's going to hash to the exact same counters. Okay? So on update, this is on insert, this is all I do. For each of the rows, I hash to one of the counters, and I do an update. So for each row, hash to counter, do, and so do an increment. All right, so this is all I do in the stream. Again, it's fairly simple. Okay, and then I have to handle a query. Okay, so I have a query Q in M, and so now the output of the query is going to be this FQ hat. Right, so I have to output FQ hat. Right, my estimate of the counter at Q. Okay, so I'm given a query. So what would I do to extract an estimate? Yep. Yeah. So okay. So I would run it through every hash function, and the first guess is to take the average of the counts. It turns out the average is not the best thing I can do. I can do something smarter than the average. I want to run it through all the hash functions. I want to do something like some operation over j in the set T of all of the h of j q's. Right? So I want to access all of the different counts associated with the query. Right? I know where, if that element came in, where it would have hashed to. I can take the average over all of them. It turns out doing the average is actually going to be so slightly wasteful. There's something. Okay, so for each of the counters, is it ever going to be smaller than the true count? Let's say I've only added things into it. Is it ever going to be smaller than the true count? No, it has to store everything. If I look at a certain IP address, say the IP address of my computer in my office, right? Every time for every row, it's going to get all of the instances of that IP address, but it might get more. I might have some collisions on the hash function, and those more will only increase the estimate. They're never going to decrease the estimate. Yeah, right. So instead, I can take the min. I can take the min operation, the min over all these counters, right? So that's why it's called the count min sketch, right? And so it's taking the min over these, and they're all overestimates. So whichever is the smallest, it can't be an underestimate. So I might as well take the smallest one.
So this algorithm doesn't have a replacement policy?
Yeah.
Okay.
Yeah, it's kind of overloading everything. It's throwing everything into the same table. Yeah. Other comment? No? Yeah?
Did you get argmin?
Well, if I took the argmin, I would return the index. The argmin returns the index j, right? I know this is confusing, this notation. The min takes the actual value of the function, and the argument returns the argument, which would be like 2. But 2 doesn't tell me anything about the actual count. The count might be 3,000, right? But it's well as the second one, right? So that's, right. So I actually want the value. Yeah, good. That's great. All right. So this is the algorithm. It's, you know, again, it's a fairly simple algorithm. You're going to implement it in your homework. These hash functions are going to be like a uniform hash function. You'll need 5 hash functions. So you'll again have to probably do a trick with by adding a salt onto everything in order to do it. Or you can, I think you only need 5, so you can find 5 different functions, SHA-1, SHA-2, SHA-3, SHA-4, SHA-5 if you want to. Doing something like this will also work. You need it to map to only k things though, right? Okay, and it should be this uniform sort of, or these perfect sort of hash functions. We'll assume it's a perfect hash function where that means each mapping is going to be equally likely. Or the collision of 2 things is going to be exactly 1 out of k. Right? If I have 2 things, then probably the hash, a random hash function I chose has them collide as 1 out of k. Right? Yep. Right. Whoever wants to go first.
I was just wondering, so like boundary condition for this structure, if we just had a single hash function, what is it we get? What functionality do we lose?
You'll have less space with a single hash function, and so you're going to have, you know, the space is then going to be basically k instead of t times k, right? But you're going to have a smaller, a larger probability of failure. In fact, the probability of failure is going to be 1/2, right? And the more as you do log base 2 of these, the probability goes down to 1/2 to the t. And I'll kind of go through this analysis next.
Yeah. At what point do we worry about maybe adding a correction? Because it's always going to be biased, right?
Yeah.
So at what point do we worry? I mean, it seems like you could even just subtract maybe the mean, like you were saying somehow, and then you have even a better estimate, and you can kind of like de-bias the.
Yeah. So I don't know if. Yeah, I've not seen that. So recently there are variants of the Misha-Gries algorithm which effectively adds some term to remove the bias from that. I haven't seen that yet for count min sketch. It might be possible. The count sketch, which we'll see next, is going to be unbiased. Okay, so there are other. The count sketch is kind of the go-to one for giving you an unbiased estimate.
Okay.
But this one is going to have a bias.
Okay.
You could try and. Yeah, we'll see next. There's an obvious guess of what the bias is going to be that you can maybe there might be some off by 1 errors, but you can probably get pretty close to it, and then you can try and subtract that. But how it filters through the min is a bit more complicated. Okay, so for any one row, the estimate you get, you can probably remove the bias. But for when you filter through the min, which gives you a better estimate. That's going to be harder to filter out what the bias is there. It's possible. It'd be a fun thing to work out. Okay, so let's one of the reasons I talked about the count min sketch, even though I like Misha-Gries and the count sketch better, is that the actual analysis is actually simple enough to understand and really illustrates a lot of kind of the ideas which are going around here. So we'll make concrete a lot of the questions you all have been asking. Right. So the first claim is that FQ is always going to be less or equal to FQ hat. Right. And right. So this is kind of, there are 2 sides. I'm going to prove now this property here with the count min sketch, that the true value is always less than the estimate, and that the estimate is never too much less than the true value by epsilon n. right? Okay. So the first thing that is always true because so this is always true because each Q always hashes to the same CJ HJ Q, right? So it always hashes to the same counter and only and it's only increasing, it only increments. Okay, I can get an overestimate because other things, the effect of other things might hash there too and also increment, but they aren't actually, so they aren't actually decreasing. I mentioned it can work with subtractions as well. This will work within what's called this like turnstile model where all the counts are always non-negative. So think of a turnstile that I don't know if they still have it at like the football stadium but they used to be, there's a thing that you walk through the gate when it goes in and it counts when you go in, and when you go out, you turn it the other way. And but the number of people in the stadium is always non-negative, right? Someone who walks out must have walked in earlier. So as long as the counts are always positive, I can do subtraction, and I've only incremented things. Okay, so this is the left-hand side. The right-hand side is a little bit trickier. Now I want to say that FQ hat is less than FQ plus some W, and I want to say now say W is less than epsilon n. Okay, and this will be basically less than epsilon times F1, which is right. So and I want this to be true with probability greater than 1 minus delta. Okay, so let's first look at this for just one row, right? So let's say one row so hash function. Okay, and so what I'm going to do is I'm going to create a random variable. So Wj. Okay, so this is going to be equal to Fj, and so this is for j in M. So for one of the other elements, I'm going to bound the overcount. The overcount only happens when a different IP address hashes onto my IP address, right? So a different element hashes onto mine in this one row, right? And so it's going to be Fj if h of, I overuse j here. Let's say okay, let's say this is going to be Fs if it's going to be Fs if Hj of if this hash function, which we'll just call H, there's only one hash function that we'll worry about. So H of S equals H of Q. And so this happens with probability 1 divided by K. Okay, so if I have a collision between element S and Q, which is the one I want to estimate Q, okay, if I have a collision, then my overcount for this one hash function is going to be all of Fs. The hash function is deterministic, so every time an element S comes into it, it's going to overestimate. So I'm going to get its full count, and it's going to be 0, so otherwise. So if I don't have a hash collision, then this value is going to be 0. Okay, and so this is a random variable based on the choice of the hash function. The random choice of the hash function is give me this ys, and that's going to be the overcount caused by element S. Okay, and so then I'm going to have this x variable, which is going to be the sum over S S in M, where S is not equal to Q, which is going to be the sum of these YS terms here. Okay, so I'm going to sum these all, and this will be the overcount from all the elements, right? So if I can bound, so I'd like to bound the expected value of this, right? So the expected value of the overcount X is going to be the expected value over the sum S of YS, which is, I can factor out this sum, right, by the linearity of expectation, okay? And the expected value of y of s is exactly going to be equal this sum over these terms s is going to be f of s divided by k. Right, the expected value of this random variable y of s was the total count of the frequency of all the terms that occurred which are f's times the probability they're a collision, 1 over k. So f of s over k. Okay, and so this is the sum over everything except q, but it's basically f1 over k here. This is basically f1 over k. This is a slight overcount here because fq doesn't need to be included. So I can ignore the one, my own count, which is not an overcount. But it's, hopefully there are lots of other things. So this is the one that's important. Right, so this is f1, which is n over k. Okay, so all right. So what I can say is that the expected overcount for one so for one hash function is going to be upper bounded by f1 divided by k, and this is equal to n over, and I set k equals to epsilon to 2 over epsilon. Okay, so this is going to be epsilon n over 2. Okay, the expected overcount of one hash function is going to be at most epsilon n over 2. Okay, I wanted that with a high probability that this was going to be in most epsilon n, and for one hash function, this happens, the expected overcount is epsilon n over 2. Okay? Now I want to say, what's the probability that I get more than epsilon n? I'm going to use what's called the Markov inequality. Okay, which says if I have a random variable x with the expected value of x equals alpha, then the probability that x is greater than I shouldn't have used alpha there. So with expected value mu, the probability is greater than alpha, and the random variable is greater than 0. Probability it's greater than alpha is going to be mu over is going to be mu over alpha. Okay. This is basically, if I know it's greater than 0, that the probability that it's going to be so much larger than the mean. Let's say this is twice the mean. Okay, then this is going to be 1/2, which is the case we have here. In this case, we have the expected value is epsilon n over 2. That's the expected value of x. And I want this to be epsilon n, right? I want to say the probability that my overcount from one thing is more than epsilon n. That's the bound I wanted. So I put that for alpha here, and this is equal to 1/2. Okay? So now I can say the probability one counter has W, remember W is this term here, greater than epsilon n, is less than or equal to 1/2. Okay, so for one counter, question before, I have, by setting k to be k to be 2 over epsilon, the probability I have more than epsilon n there is going to be at most 1/2. And a simple application of this Markov inequality. Okay, so now this was for one hash function. What do I get out of having these t-hash functions? Right? So now I've got t hash functions, and to summarize, for one hash function, I have the probability that, hash function, let's call this hj, for that my estimate overcount wj for this one hash function is greater than epsilon n. This is less than or equal to 1/2. All right, so now I've got these t-hash functions, and I want to put this together. What happens when I have t-hash functions? The t-hash functions are chosen independently. h1 up to ht chosen hj from some family in the pendantly. Okay, so I would choose them independently. Just kind of different salts effectively should do this for you. So that means that I can, if I take the min, it's only an overcount by more than epsilon n if they're all over that, right? So they all would have to fail. So what's the probability? So with let's say with t, so hash functions, then I'd say w equals the min over j of these wj. I only have w greater than epsilon n if all wj greater than epsilon n. If any of them is less than or equal to epsilon n, then I take the minimum. So this is why I take the minimum. This is why it's not feasible, right? So what's the probability that none? So the probability of failure occurs if they all have more than this error, right? So let's call this pj, and so the probability that w is greater than epsilon n is then going to be equal to pj to the power t, because these are independent things. When they're independent, I can take them to the tth power, and this is going to be less than or equal to 1/2 to the t. And remember, I set t equals to log, let's say base 2 of 1 over delta. Right, so this is, and so 1 over 2 to the log base 2 of 1 over delta is going to be equal to delta. Right, the 2 to the log base 2 cancels. I get 1 over delta. I'm going to get delta, my probability of failure. Okay, so the probability that they all fail is going to be delta if I set t equals to log base 2 of 1 over delta. Okay, and so I can make that I can make this probability of failure pretty small because it's wrapped inside this log function. So in your homework, we use t equals 5, and 5 to 10 is typically what's used here. Okay, good. So hopefully for those of you who had these driving questions of why we need all these things and want to see the analysis, this is a pretty clear analysis. You know, other algorithms in this form are going to have kind of broadly thematically fairly similar analysis, but they're usually more complicated. This one is a pretty straightforward kind of one I can do in class in 20 minutes. All right, so this is one of the few times I do a proof in class. So, all right, okay. So I want to talk about 3 things quickly the last 20 minutes. Yeah.
Yeah, I have a question. Is it possible to like somehow only keep track of like the last million objects from your stream? Like, let's say you're just gonna have objects coming in constantly, but you really only care about the most frequent ones, like the most recent ones, not frequent.
Yeah, so there are these things called sliding windows in streams. And so people have studied these where I have a sliding window that only contains the last so many objects. And there are a variety of strategies for having these sliding windows algorithms. And this has been studied, and there are a variety of tricks. I'm not going to get into them. I'd say what's actually almost as natural and is to actually, and is idea from that you might see in like an AI class, is that you want to downweight all the previous things. And so I want to take my whole sketch and multiply it by 0.99 or something like that. So it's important that everything that occurred before is decaying. And so the things that have occurred way back, they have been multiplied as 0.99 many times, so they've decayed a lot more, and they eventually kind of dissipate. But the newer things have not been decayed as much yet. So you have this, and this is much easier to implement and gives you a similar sort of feel without having, there's some complexity in these sliding windows approaches, but there is a family of techniques for dealing with this. Yeah. It's a good question that comes up a lot. That's my simple answer for you. Yeah. So the first thing I want to say is the count sketch. And so typically if class teaches these, they usually do the count min sketch first. It's a little simpler conceptually. The count sketch actually was developed several years before that. And it's slightly more complicated. Instead of, I'm still going to have these counters C11, C12, up to C1K, the same as before, and CT1 up to CTK. Now I'm going to set K equals to, I think, 4 over epsilon squared, and T is going to be equals to, I think, log, again, base 2 of 2 over delta. So these parameters are slightly larger, including an epsilon squared inside of here. Okay, and so I'm still going to have these hash functions, which are going to go, each hj is going to go from m to k, and these are going to serve basically the same purpose here. So all of this is the same, but I'm also going to have t of these, space. Okay, so I'm also going to have t of these sine hash function. And so these are going to go sj, and these also going to go from m, but they're going to go to -1 and +1. Okay, so I'm thinking of putting these one here, that's up to st. Okay, so this is basically the same, but instead of doing a count, so now on an insert, and I'll do this for A, which is an A and an M. So if I'm inserting M, I say for J equals 1 to T, I'm going to do C J H Hj of A. So I'm going to find the appropriate counter, and I'm going to set this to Cj Hj of A plus the sine fj of a. Okay, so what it's doing is I'm either adding or subtracting. Either add or it's going to be subtracted. Okay, so this is a consistent thing. I've drawn S randomly from a hash family, but then it's fixed, right? So that means every time I see A and I go to this counter, I'm either always adding it or I'm always subtracting it. So sometimes it's building a negative count, sometimes it's building a positive count. Okay, so this is the insert. Then on a query for a Q in M, I'm going to return FQ hat is then going to be over J in M of Fj Hj of Q. What operation am I going to use now? Using the min is not going to be great because I could have an overcount or an undercount, because I could have a bunch of things which have been subtracted from the count, right? And I'm going to multiply this, actually, this value multiplied by, okay, so I'm undoing the sign. If this was of Q, if this was a positive 1, then this doesn't do anything. If it was a negative 1, then the count I estimated from there was negative, so I'm undoing it. I'm multiplying by -1 to get back the positive count. Okay?
So you want to take the median?
Yeah, right. So now I want not the average, but the, so now I want to take the median. Usually you don't write it this way. I probably write it as a set and then take the median, but I'm taking the median of these things. Okay, so I want basically, so now what's going to happen in the analysis, and this is why this median is why I need this 2 up here. Because of the median, I'm going to say, well, this is going to fail if I have too many things which are an overcount or too many things which are an undercount. And so I have log of 1 over delta possible overcounts and log 1 over delta possible undercounts. Right? And so the 2 up there allows me to take the median, and this kind of covers both sides. But I need a little bit extra up there. Yeah.
For your sign hash function, do you randomly how do you?
Yeah. So it's so that's a good question, right? So I kind of glossed over that, but both of these both are chosen randomly from a hash family. Okay, so we talked a little bit. I mean, hopefully in a data structures class, you've seen how to get the first sort of hash function using a hash table. With the sign hash function, there kind of lots of ways I could do that. I could do the same way as I did the first hash function, but set k equals to 2. And if it indexes into the first one, it's a +1. If it indexes the second one, it's a -1. Right? So that'd be one way of doing it. Or I can do another thing that gives me a bigger thing, and the evens are plus, the odds are minuses. There are different ways of doing it. There are also probably more direct and simpler ways. Okay, but yeah, again, it's chosen as deterministic once you choose it, but it's chosen from this kind of random family before. Okay, and the analysis gives you an estimate on, again, this is going to say the Fj minus Fj hat is going to be epsilon times F2 with probability greater than 1 minus delta. Right, so I'm going to get, this is giving me this F2 error, but I have k equals to 1 over epsilon, 4 over epsilon squared. So k seems to be a bit bigger, but then the error I get is dependent on this other quantity. So when things are very skewed distributions, then this turns out to work, often work slightly better. It's not too much harder than the count min sketch. Again, should be pretty simple to do. But I'm not going to go through the analysis of this one. So cool. So all right, good. There are two more things I want to mention quickly. So another one is so these things called Bloom filters. So how many people have heard of a Bloom filter before? So a few of you have, and these are kind of conceptually similar data structures, which I think are much older. These were developed in like those sketches in the early 2000s. Bloom filter dates back to like 1970, I think. And so this is a set data structure. So again, it's going to be a sketch sort of idea, and it will tell you. So it's going to store. It's going to have. So if some query, say in M, is let's call this B, is in B, then it reports. So it always reports that's in there. If Q is not in M, then it so usually says not in B. But so this usually, it sometimes has these false positives. So it has false positives where it says, well, I think it's in there, but it's not actually in there. There's no false negatives, so it never says it's not in there when it actually is in the data structure. But it's this sketch representation. It uses hash functions.
Should that be Q not in B?
Thanks. So if Q not in B, right? Yeah. So if Q not in B, then it usually is in there. Great. Okay, and so this is similar in principle to like say the count min sketch, except it's going to store bits. Okay, so it's going to have these k bits. So it's first going to set them all to 0. Okay, and instead of a counter, it's just storing a bit, so it's even more compressed in that way. And then it's going to have t hash functions. And each j is going to go again from m to this going to k, but it's only got one string of hash functions. Okay, so on an insert for j in t, it's going to set the bit of hash of j of on an element. It's going to set this 1. So it starts at all zeros, and when it inserts something that's set, it sets all the values 1. So it's going to go in, and it's going to hash to these different things and set these values 1. If they're already 1, it keeps them 1. Okay? And then on a query, it says if all h of j of q equals 1, then say yes, that's inside. Okay, and if they don't all, then it says no. Okay, so this is a common thing that's used in networking and monitoring kind of large sets in various ways. And it's slightly different. And I just mention it just to give you a kind of a, the count min sketch seems to be more useful and the count sketch more useful in these more data mining sort of analysis, but this is a much older structure, so I often get questions about this. So it puts all the hash functions into the same array, so it kind of overlays them on top of each other, and only uses bits instead of counters. So it only says whether something's inside, not whether, not how many times it occurred. Okay, but it's a similar idea, and this is maybe kind of influence some of these sketch data structures. Okay, and then one more thing that is, I want to mention the a priori algorithm, and this is for frequent item sets. And so if you took a data mining class like more than 10 years ago, maybe even more than 5 years ago, or at some other universities, they would spend like several lectures on this. This is a different problem. I don't think it's used very much anymore. It's not necessarily statistically robust in what sort of analysis it does, but it kind of fits this theme, so I'm going to mention it for 5 minutes, and there's some ACM kind of guide of what should be taught in a data mining class, and this is in it, so this is my 5 minutes. Okay, so this is, you can think of having kind of it can be a stream or a set, right? So A, but each element A is actually going to be a set of, say, let's say B1, B2 up to B T, where each Bj is in M. Right, so this stream or this set is A1, A2, up to AN. Okay, and so each of these elements is a whole set. So think of it like you go to the grocery store, as a common example, and you buy, and every customer buys a set of items, right? It's usually a fairly small set, 20 items, but it's not just a single thing. So the grocery store has all these products that they sell, and some of them, you want to find ones that customers tend to buy at the same time. So I want to find frequent item sets, frequent subsets of shopping lists that are bought together. And the old story goes, and I've got lots of applications for grad school that start with the story about that people found that beer and diapers were often bought together on the same thing. The idea was often the dad would run to the grocery store to get diapers and would grab some beer at the same time. And this shows up in kind of this very classic description of this algorithm. It may not actually be a true co-occurrence, but that's how it's usually taught. So now you've been told that story. Okay. Okay. So what's the algorithm of trying to do this? Let me quickly go through. Okay. So think of this as the data set here. Okay. So I've got data set here, and I want to find the frequent item sets. And the idea is that if there's a pair or a triple that occurs together a lot, then individual elements occur together a lot. So I make these passes on the data, and I do a frequency estimation on each item. Right, so let's just say I want to find sets that occur more than 1/3 of the time. So then I first only find the items which occur at least 1/3 of the time. Right, so the items kind of 1 occurs a lot of times, 2 occurs a lot of times, 0 only occurs twice, so it needs to occur at least, I want things that occur at least 4 times. So let's say I want at least 4 occurrences. So I pull out 2 occurs more than 4 times, I think. 3 occurs more than 2 times. I think 6 and 9 are the other ones that occur more than 2 times. Okay, so this is pass 1 and 7. Okay, so this is on pass 1, and I could use one of the other algorithms to do this pass if I wanted to. Okay, now on pass 2, I look at pairs from above. So I look at 2, 3, 2, 6, 2, 7, 2, 9, 3, 6, 3, 7, 3, 9, 6, 7, 6, 9, and 7, 9. Okay, and now on the second pass, I care about, do these co-occur together, like 6 and 7 co-occurred here. And I only have to check these pairs because 5 and 7 could not have co-occurred together more than 4 times because 5 didn't occur 4 times. So I filtered out a lot of the things, and this hopefully doesn't grow too much. It could be at most n squared, but hopefully it's some value k squared, and k is small enough. And so then I filter, and I think the only one that occurs more than 4 times is 6 and 9 from when I've done this example in the past, and then I can stop. Okay, and so, right, so let's say 6 and 9 occurred here, and here, and here, and here. So this occurred 4 times, but nothing else did. And then I know no triple can occur together 4 times because I would have had to have the 3, let's say 7, 6, and 9 all occur together as a triple 4 times. So that would only happen if 6 and 9 and also 7 and 9 and also 6 and 7 co-occur. So it allows me to filter, and usually the second or maybe the third pass is the biggest pass. And then things get smaller and smaller. And so this was kind of an old school data mine approach, but this idea is kind of very powerful in that you can iteratively filter out things as you're making passes over the data. All right, okay, so I just want to quickly mention this. And these ideas are actually used in graphs to find cliques and stuff in graphs as well. There's similar sort of analysis and ideas that show up there and other similar places. Okay, great.